Go ahead, Ben.
Cool. So, well, one, thank you all for being here. I know things are running a bit late. I'll try and make sure this has got at least a bit of a gap at the end of it. I'll be here afterwards anyway, so happy to go into detail. So, this slide has Flink Forward written all over it, because last week was Flink Forward, and that was great fun. And my lovely colleague Karen actually opted me to do this one rather than herself. She's normally on the West Coast, but she's currently in London, where I normally am, having a wonderful time. So, I'm here to talk about VERA, the engine that revolutionizes Apache Flink. But let's start with who I am. You kind of had a brief intro to me this morning as the field CTO of VERA. My name is Ben Gamble. Hi. But I just tell you a bit more about what I actually do. So these days, I tend to go online by the technology sommelier. And it's really my job is to pair technologies. I talk to a lot of people. The CTO bit is often the chief talking officer. But for me, it really comes down to no tech sits alone anymore. You don't just build a monolithic stack of your own things from zero, you put things together. And last week, this was quite good fun. It involved pairing mainframes and COBOL, Apache Flink, and hopefully a trip to Machu Picchu soon, because we were dealing with Peruvian banks, their COBOL stacks, and trying to remove MIPS from their processing lines using Apache Flink. I kid you not, this was COBOL on a whiteboard last week. This is my new achievement, because last time I used to give this slide, it was programming Pascal within the last 18 months. Now I've got COBOL within the last 10 days. So, just to show you, things never die. They just keep coming around again. So, I'm all about terrible jokes and fast data. And the jokes will be terrible. I do not apologize. And you will have been warned. But also the fast data things. So I spent a lot of time working with interesting open source techs. So a while ago, I used to work at a company called Ivan, who had 11 products, which I used to call the herbs and spices, because we had the KFC stack with Kafka, Flink, and Lakehouse. But these days, as I kind of tend to work more with Pulsar, we kind of went to Montreal and Quebec, where they call it PFK instead, with our Pulsar, Flink, and Kubernetes. Yes, I went that deep on it. And these days, I'm also a keeper of ducks. In my garden, there are 3 pet ducks we've had since Easter, and if you're ever on a video call with me, every now and again you'll hear quacking. These are literal ducks. Sometimes I pick them up and they say hello. So, who here, by a show of hands, knows who the VERA are? 1, 2, 3, phew, cool. So, to start with, the VERA means squirrel. If you put into Google Translate, it will pop up with one of about 3 Eastern European languages and tell you it means squirrel. The squirrel was the messenger on the world tree Yggdrasil from Norse mythology, hence made sense if you cared about transmitting data. It was once called data artisans, and for the longest time, I knew data artisans and didn't know Viverica. They were very quiet about the name change, to their detriment. We're trying to fix that. And they were the original creators of Apache Flink. Apache Flink came out of a project called Stratosphere in a Berlin university. Roughly the same time, Spark came out of a project in a Californian university. They're a world apart, similar mentalities, similar attitudes, wildly different trajectories, and quite different technologies. And we're kind of nuts about data. The key thing really here is that Apache Flink started out as a way to do ridiculously large processing of data. The streaming bit was kind of added to handle larger than memory data because nearly all databases these days stream at some level or another. If you've got to pull from a disk, you may as well pull it in a stream and process as it goes through operators. So a bit of a table of contents, what's happening. There's going to be a bit of an introduction, some history, what is VERA, the kind of core pillars of VERA, which you heard about earlier, and then what does it solve for, and maybe some Q&A in the middle. Though, depending on time, we might do that at the end. So, a bit of an introduction. Apache Flink is that de facto standard for stream processing. It's kind of just become a thing over time. Most of the biggest and most challenging use cases in the world use Apache Flink to do their real-time processing. There's nearly 2,000 companies using this kind of publicly and admit to using this. A lot probably use it and don't admit to using it, but that's just the way of technology. And historically, state management, as of like 2017, was kind of a thing because they brought in RocksDB, and it was a really powerful thing. But RocksDB is still based off the LevelDB, based off BerkeleyDB paper from yesteryear, and hasn't really changed much since then. And this is where we kind of run into a little conundrum, which is tech has changed over time. The systems we run on have changed over time, and more importantly, so have how workloads. So it didn't really hold up in the same way. You had the ability to run, on multiple machines. Great. We didn't have as many machines as we do now. And then it's bigger CPUs. Brilliant. Things go faster. Bigger disks. Brilliant. We can store more data. Then it's like, wait, how big are disks? Well, they're not as big as the data. Data went up even faster. So there's a load of these things don't hold true. The assumptions were made at the beginning of these projects. And even the assumptions we made halfway along these projects often had to change. And this is where VERA came from. VERA was designed to be a cloud-native engine built to adapt open source Flink into the modern era. When you start trying to change the kind of foundations of one of these projects like Flink, you say, OK, what needs to change? A bit like Urza, where they took out the consensus protocol and Zookeeper and everything else, and said, what happens if we do that, make it leaderless? That's a big change. In Flink, it was similar. Flink came from a lot of these older school spinning platter devices. Data sets were pretty unchanging, to be honest, and the flexibility just wasn't there. Also, they came from the days where you bought your metal. You had a capacity. To install new capacity and scale up a job, first you had to go talk to Dell, and that took time because there was a shipping time involved. So the ability to aggressively scale up a job was just not a problem back in 2011, not in the same way. So we changed it quite significantly. And a big core of this is a new state store called Gemini, which is an enterprise state store inside the VERA runtime. So VERA is the VERA runtime assembly. At its core is a state store known as Gemini, and there's a lot of other additions along the way. There are 3 core pillars, and we're going to explore them as we go. Streaming data movement, real-time stream processing, and the stream house. Combined, these pillars are tailored for seamless support of data ingestion through connectors, stream processing in real time, what Flink normally does, and streaming Lakehouse architecture. So let's start at streaming data movement. Now, the core here is connectivity, because unless you can pull data in, you're kind of not doing very much. And like the ubiquitous old USB-A problem of plug it in once, no, just flip it over, no, flip it again, maybe approach, if you can't connect to data, you're in for a bad experience. And because data comes in multiple different ways and multiple different speeds and reliability, there was a need to have a hardened system to ingest this. For example, you're buying tickets. You bought a ticket for a sold-out show. That ticket needs to be good at the door, or you're going to have a problem. It's stuck in a queue trying to rebuy your tickets because the database from A did not sync to the database from B. Or you're trying to buy goods online, and suddenly your ticket you bought has been bought by someone else. This is often a problem with Taylor Swift, particularly online. They broke Ticketmaster. You try to purchase a ticket, it might have been pre-sold by the time you got to the thing, and this is because you can't get data out of one system and into another system. Now, Flink has long been an excellent tool for moving data from place to place and compute with it, but as performance needs increases, you needed a more concrete framework. So let's dig into it a bit deeper. So a classic example is, you've got a data system, and you've got users, payments, and reporting. So, with users, you might choose, Postgres, pretty decent database, very good for transactions. And payments, Postgres also works quite well. Nice transactional support, really good scaling. However, what happens next is then you're making reporting, and nearly always in companies I've seen, they start using Postgres again because it's there. And this is where you start kind of wondering what happens next. And hands up if you've seen this before in a real-life system, which is queues in Postgres. Because this literally happened in a place I worked quite recently, where everything ended up being a Postgres problem. And the real thing about this, as we've learned, is the right tool for the job is important. As we scale up, we can no longer rely on these magical do-all-things systems. So we end up with a lot of different databases. You've got your transactional databases with MySQL and Postgres, Oracle if you can afford it, and Redis if you're feeling brave. And then you have your kind of streaming systems like Pulsar and Kafka, and your more analytical tools, either for 1 to 2 users or for many, many users, like Pinot, Doris, Startree, and ClickHouse. Now, the key thing here is that streaming data movement is about connecting these systems. It's an enterprise version of the Flink CDC tool we open sourced earlier in the year, and allows you to move and create whole warehouses in a single select statement. Also define YAML-based pipelines between end-to-end systems. Because what matters is putting the data where it needs to be for both storage and action. But in addition, you can power event-driven apps along the way because you've created a stream. As soon as you've started pulling data out of these systems as it lands, you have a stream of data. And there's a fun guy called Gunnar Morling I would recommend you chase up with the Debezium project if you want to know more. It's really cool. So now the data is moving. What can we do with it? And this is where we get to the second pillar, real-time stream processing. And the first question you got to ask yourself is, what needs to be real-time? And what real-time really means? In the context of this, we're talking about what is often termed soft real-time, which is as fast as possible inside reasonable SLAs on commercial off-the-shelf software and hardware. Hard real-time is nearly always defined as a hard limitation, an SLA with an absolute definition and a margin of error, nearly always handled by physical chips, which have things like watchdog timers in them. So, on that, what needs to be real-time? A lot of times it's chat. If you're chatting with someone, there's a maximum amount of time you can wait for a message before you think the person's ghosting you, ignoring you, or put their phone down. If you've seen those little 3 dots go on WhatsApp or equivalent, and they take too long to appear, it feels like they're not taking you seriously when they come back with the one line, okay. Things like stocks. If you're trading, particularly if you're doing consumer trading, but if you're doing professional trading, it's even worse. If you can't go fast enough for that data, you can't make a real decision. And you also don't feel confident that the price is real. And maps. If Waze told you that the crash that happened this morning happened now, that's kind of useless. If you can't move the data at the right time, it's not relevant. The actual value of data can often decrease rapidly from the time it was created if you can't move it in real time. But let's say, why use VERA? As we've already found, you need things to be in sync. It's not worth buying something if you can't know the inventory is there to begin with. And as things scale, you need to have the ability to connect them carefully. So your bank balance not being correct means you can't pay your rent on time because it didn't get synced in time. Things need to be in order. It's a bummer to pay for something when your balance hits 0 because the payments didn't come in before the payment went out. Now, by having the ability to have larger than memory state in this new enterprise state store we built, which allows for both disaggregated state and tiered storage and smart key sharing, you can now have a larger grace period. So you can now reorder things into the gigabytes and terabytes rather than just in the megabytes. And most importantly, things need to be predictable. VERA ships with an SLA meeting autoscaler. So hands up here who's used an autoscaler for a system, maybe in Kubernetes. Yep. Now, hands up here who had to just scale it off, let's say CPU usage. Yep. Or RAM amounts or some sort of load. How many of you would have liked to scale it off an SLA like round trip time? So you know how long it took for a job to finish. So we built that. By having Flink exposed on the inside, you can start doing things like time, the amount of time between operators, time back pressure, and have a nice heuristic on what meeting an SLA really looks like. So we give you the ability to define a goal SLA, like 1 minute end-to-end pipeline, 1 second end-to-end pipeline, 300 milliseconds end-to-end pipeline, and the ability to auto-scale to meet that. Now, it will then throw errors if you try and make it scale a job that has a 10-minute window to having a 1 second end-to-end. But that's design. So this is one of the really powerful features in VERA, is the ability to kind of meet this stuff as you want. So to kind of recap, it's the ability to get data when you need it through Flink CDC, to have fast storage for shuffling late data and do joins at high speed using a disaggregated both state on both disk and on object storage, but also separation of keys and values so that you can do much faster SQL joins. And also the ability to scale to meet SLAs rather than just CPU targets. Many a time I've used a thing pinned at 100% CPU, and it's responded just fine. That isn't useful to me. I only want it to scale when I actually need it to scale. And if I'm starting to get latency spikes, I need to meet those quickly. So now let's talk about the Streamhouse. Now this one's going to be a little bit short because I'm then going to talk about it in a great deal soon. So, and this is originally the title of the next talk, which is Who Said Data Lakes Need to Be Slow? So I'm going to gloss over some details as I go, and then talk about them in depth in about 5 more minutes. So everyone here has probably built a data lake. And a lot of people had data warehouses at once, because we need to make strategic decisions. And this means we need to have access to all our data as fast as we can. Because originally, when S3 became a thing and HDFS was just available still, data became a dumping ground. You built these mountains and piles of stuff, and eventually querying it became a problem. So, we started with the warehouses, too expensive. Data lakes, schema on read, hope, not a great experience. And then the Lakehouses started to kind of find that middle ground. But the problem ends up being is that there's a lot of work to be done to massage that data into better shapes. Even Parquet files aren't perfect. You still have to go find the right version, find the right schema, find the right file. And with tools that do merge on read, like particularly Iceberg and Hoodie, this can often take a while to do all the merging you need to get to a realistic view of your data. So this is where Apache Pymon comes in, and I will talk about that in a great deal later. But just to give you a kind of a quote here, right? So this is AutoHome in China. They are doing real-time recommendation, and it took them a day or T+1 to get their recommendation, or maybe H+1 or an hour to get to the answer they needed after the first upgrade. But with Pymon, they were able to get to single-digit minutes, thanks to Apache Pymon's partial update features. So we'll go into Pymon in a bit. But the idea of a Streamhouse is the ability to have Lakehouse level storage with data warehouse level speed and performance, having partial updates, but also the ability to have a message queue level kind of performance by just incrementing things along the disk. Because Streamhouse goes really, really fast, having an up-to-date Lakehouse in single-digit seconds instead of minutes, hours, or days. Now, to wrap that up a bit, VERA is built on these 3 pillars, right? It's important that we're not saying goodbye to open source, because VERA is also the test bed we do for a lot of open source things, because it's 100% compatible with open source Flink on the version it is pinned to. And Flink being de facto powerful means we can make it better. And from that point of test beds, disaggregated state is coming in Flink 2.0. It's not quite the same engine, but it is a version very similar to the one we tested in Gemini. And of course, Flink CDC, we've had that for ages, but is now fully Apache under the Apache umbrella, and it's under the umbrella project of Apache Flink. Real-time stream processing is just Flink itself. And the Streamhouse was originally Flink table stores and is now called Apache Pymon. There is a demo, but I'm going to shunt that to the end because of time. And just a quick thank you to Karen, who was the one who suggested I do this talk in the first place. She used to work at Stream Native, and she is awesome. When we did this last week, she was on stage with me. And just because she wanted a holiday in the EU while she was there, I elected to be the one flying out. So a bit more resources. If you want to read the white paper on how it all works, there's the link. Once again, come find me afterwards if you can't find it quickly, or just look on our website. It'll be there. The cool thing here is that we explore in quite a lot of detail in what it can do, how it's been built, and why. And there's a kind of a long blog series where you may hear me talking a bunch about how to get started with VERA and what you can do with it. A core problem with a lot of these things is, unless you lay out some use cases, you don't know what it's for. And with that, I'm going to say thank you and give you 2 minutes before I start talking again. Cool. So this is my next little bit of a talk, which was originally part of the ending of the previous talk and also a different talk on Apache Pymon. So who said data lakes need to be slow? Now, this character is called Pymon as well. And if you've ever played Genshin Impact, that's where it's from. But this is the real logo. It's some sort of fish, which I was told I've never remembered the name of. So, hi, I'm Ben Gamble. I do things with Flink. You may have heard of me. I may have said this earlier. So I've only got one slide about this. So let's talk about managing data at scale. So it was about 1956 when the first megabyte hard drives were out. And this was a massive deal. I think they costed $40,000 in that day's money, which is about 30 million today or something. And then if you skip forward a bit to 1980, the first gigabyte hard drives. So it didn't take long for things to get big. And 81 was that kind of famous apocryphal, apparently, quote of 640 kilobytes of memory being enough for anybody. Bill Gates denies this, but I find the myth to be amusing enough that I will keep it alive. And then of course, it was in 1999 when the first gigabyte RAM sticks started being sold, which is a big deal. The term big data actually comes from 2001, and we'll talk about that in a minute. Then 2007, it was the terabyte hard drives, and then today, your mobile phone has a terabyte of space on it, and many, many gigabytes of RAM. So so you can start to see it scaling. But let's zoom into big data, because big data is where the Lakehouse was born. Now, big data was coined by Gartner, of all folks, and they said the 3 V's of big data, which were volume, velocity, and variety. And because analysts never want to say just one thing, they added 3 more and said it was about the veracity of the data, the variability of the data, and making value from the data. Now, in this case, I agree with all the principles at heart here, which is data is big when it's a lot of it, the volume. The velocity makes it hard, and the variety means you can't just have generic, oh, it all fits into a schema. This kind of broke up the age of disco in the relational database in a big way. So the next question is, of course, is where does that data live? And big data originally kind of lived in the warehouse. And data warehouses were powerful. This is where the term cubes and things came from. But they were hell of expensive. If you've ever seen a Teradata bill, you'll understand that bills have more zeros than you thought you did on old school software contracts. Like, we wish we could bill like Teradata used to bill. That would be fun. We'd get paid. But no, these days we have to be a bit more thrifty than that. And then the data lake came about by saying, well, object storage is cheap. We can just dump it and then schema it up later. And this was true and is still sadly true. This is where the data wastelands came from, the swamps, because all the tools that said they could schema on read never quite were able to deliver what we thought they did. And then lastly, the Lakehouse, which was this kind of way to say, what happens if we bring the metadata from the warehouse and some of the storage formats we know well, and basically say that, we'll bring a query engine separate to our storage. Kind of the logical extent of decoupling storage and compute. So what powers a Lakehouse? So a long time ago, it was Hadoop. So the HDFS file system was kind of the first point of call in what I would consider the early parts of the modern warehouse. HDFS was a replicated file system that allowed you to store stuff. The Parquet file format, which is still used to date, came from this era. And once you kind of realized you could crunch this with many different pieces, Hive kind of became the de facto data lake/warehouse people were using. And from then, Spark appeared, and from Spark plus Hadoop, you ended up with Hoodie. Now, these are kind of the logical little progression of things. Hadoop came first. It was MapReduce. 8 years ago, it was their 10-year anniversary. And one of the guys out on stage with me last week was saying, this is the second 10-year anniversary I've been to, but how things have changed from the Hadoop 10-year anniversary. But Hive is still not dead. It's still around. And a lot of these kind of tools came to mimic it. Iceberg is effectively just a rebuild of Hive on slightly more sensible principles. Hoodie basically said, let's embrace Spark rather than Hadoop, but it can also use Hadoop, and basically uses Spark as an engine to correct its file format as it goes. Very powerful, very expensive, reasonably fast. And as you kind of move forward in time, you kind of think, were there any other options? Now, from Flink, there was something called, well, this is what we call the Streamhouse, but this was the table store originally. So this was a sub-project in Flink, and it was an extension to give Flink the ability to write to these, to write some level of stuff to an object store to allow for streaming queries and external query engines to have some state. But we like to unify things. So with our unified CDC ingestion, Flink unified compute with batch and stream, and then Paimon came about because we wanted to have unified storage to go with that. So the reason Paimon is fast is the same reason that data warehouses is fast. So hands up here who's familiar with the log structured merge tree? Few people. So the idea really is that as you write data, you want to write it pretty much immediately. But the fundamental fact is, as you then have duplicates of that data, that's hard and annoying, and upserts are hard. So instead what you do is you basically merge data blocks together to get kind of more concrete things, and you read as you go down. You only have one version of a data per level, but what it means is over time you converge on the truth, but never stop things writing. Yes, you write more data, your write amplification, as it's called, it can be quite high, but you do not delay writing. You do not delay writing for reading or reading for writing. And Apache Paimon kind of brought this around when they decided that, hey, we can write a log structured merge tree out of Parquet files. And this is what, and if you go to the Apache Paimon documentation, you'll see they didn't even change the diagram very much. Apache Paimon uses either Spark or Flink as a compute engine to do its compactions, and basically allows you to stream data in, write it directly into a series of either append-only Parquet files or level-based Parquet files, do streaming joins and queries on it with Spark or with Flink, and then allow you to do batch queries on it like it's a standard data lake with tools like Trino, Spark, Hive. Yep, they still support Hive because Hive is still in more places than we want to admit, but also things like StarRocks and a few others. Now, inside this, Paimon is indeed that log structured thing. So it is bucketed because of the nature of things on object storage means you can't quite do as much manipulation as you can on an SSD. But fundamentally, you end up with your SST files or sorted string approaches, and you merge them down the levels. Because you don't want your Parquet files to be too huge, you do have to have multiples. If you ever use Cassandra, this is where you have your kind of max tier sizes rather than having your kind of like just endless runs. What this gives you is a lot of benefits because Parquet files come with a ton of metadata, allowing for faster queries, a bunch of the pre-aggregations like where's the max value, where's the min value, the tools you use to make queries fast. The really important thing about Parquet is that everything can read it. A lot of the optimizations that went into Parquet are used by the query engines that read Parquet, and particularly tools like DuckDB make a big advantage of this. If it worked and was fast in the era of Hadoop, when you have this many CPUs and RAM, you can do some pretty magical things. And the power of Apache Pymon is such that if you use it as a queue, it literally supports message queues. Teams like New Relic have started replacing Kafka clusters with direct writes to Parquet. In addition, as previously mentioned, whole companies are being able to make their data pipelines and their kind of ML learning jobs run in minutes and seconds rather than hours, days, and occasionally weeks, because of the ability to do rapid merges on data, on read or write, to have n threads compacting your data, because you can just put more processes against it, or scale up the compaction to whatever scale you need, particularly with the Flink compactor, and allows you to do more and more. Back again to the same white paper, as it talks a lot about Pymon, and when I wrote this, I did not know my talks were back-to-back. And I will try and do a bit of a demo now. I think I still have some time. Cool. So in that thing, I'm just going to try and do the video then. So I'm happy to show this afterwards as well, but there's one particular piece of this video which... So with Pymon, you get to do some kind of interesting things, particularly with the Flink engine. So, sorry, trying to drag this to the screen. So, can you see this? Is it visible? I can't really read it myself, but my eyes are too bad for that. So this is a single statement saying create database if it don't exist in Pymon, and we're going to create it as from a RDS catalog, including all tables. So this is one statement to import the whole of a MySQL cluster. So what happens next is we deploy that over into a Flink job. Sorry, 1 second. And mute myself. And once it's deployed into, this is our cloud thing, it works straight away in open source as well. What happens as you deploy this is it's going to basically create the Flink jobs required to pick up every table, every DML and DDL change, and live sync the data, including all schema evolutions, into directly into Apache Pymon. So as this deploys up, we'll start to see the various Flink jobs and go across. This comes with literal, every step of the way has back pressure, every step of the way has kind of bytes read, bytes ingressed, and everything else. And or automatically, as this starts streaming over, you can then start to query this immediately. Start one of these jobs, it'll be continuous. You will get accurate snapshots of data as you read it. The sync time is single-digit seconds to query, but at any point in time, it is queryable, so there's no dirty data to read. This does upserts, partial as well as complete upserts on rows, so you can do column-level upserts live with no additional complication and no additional hit on speed. And it doesn't take much resource to do this, but the rest of this is about a demo of the whole platform. So I'm going to call it there and ask for any questions. Happy to do a detailed demo live with actual code. I do have that running. It's just it takes slightly longer to do. But the key thing with this whole setup is it lets you have a live view into your real-time data. It allows you to have a data lake, which is always up to date. If you're running training or AI models against this, you can literally have all your conversations stored in real time, all the kind of lookup data with column level vector search attached, and that will be accurate to the minute or the second, depending on how much merge you want to put in. Thank you for listening. Please ask questions.